As you continue your training, you will be introduced to more advanced flight training, including maneuvering during slow flight. Slow flight can be thought of as any airspeed below normal cruise. However, during your training, slow flight will typically be conducted at an airspeed where any significant reduction in speed or power or an increase in load factor results in a stall indication. You should practice maneuvering during slow flight to develop a feel for the controls at various speeds and power settings, and to learn the relationship of power and pitch to altitude and airspeed. Before you begin the maneuver, check for other air traffic by clearing the area.
There's traffic at 10 o'clock. Let's turn right about 90 degrees.
To transition from cruise flight, first apply carburetor heat and then reduce the power to several hundred RPM below that used to maintain cruise altitude. Remember, as you decrease the airspeed, you must also increase the angle of attack to maintain altitude. During this time, use trim to remove control pressures. When the airspeed approaches the desired value, increase power to hold the assigned airspeed and altitude. As power is added, smooth application of the right rudder is required to overcome the airplane's left-turning tendencies. Then, when attitude, airspeed, and altitude stabilize, trim the airplane to relieve control wheel pressures. The attitude indicator confirms the airplane's high pitch condition, while the altimeter and the vertical speed indicator verify that you're level. At these slow speeds, control response will feel sluggish, although greater control deflections may be needed to achieve a change in flight attitude. You should apply gentle control pressures. Using abrupt movements could result in a stall. While operating in slow flight, any attempt to change altitude solely through the use of control pressures will not achieve the desired results. For example, if you attempt to climb by just increasing the pitch attitude, the airspeed will decrease and the airplane will stall. The correct procedure is to apply power, then adjust the pitch attitude as necessary to maintain the desired airspeed. On the other hand, if you decrease the pitch to descend without reducing power, the airspeed will increase above that desired. The proper way to descend is to reduce power and adjust the pitch attitude. Climbing and descending in slow flight demonstrates that power controls your altitude when you maintain the same airspeed. To turn the airplane during slow flight, the same procedures used at higher speeds are still applicable. However, in slow flight, you must add power to maintain altitude. Whenever you make a turn during slow flight, use shallow bank angles and smooth, coordinated control wheel movements to prevent stalling the airplane during the turn. Your instructor will also have you practice slow flight with various flap settings, so you can see the different attitude and power requirements for each phase of flight. To return to cruise flight, apply full power and slowly decrease the pitch attitude as the airplane accelerates. As the airspeed increases, retract the flaps if extended. After reaching your cruise airspeed, adjust power and trim for cruising flight. Maneuvering during slow flight provides you with a better feel for the airplane in various flight conditions. This will help prepare you for several aspects of flight training, including stalls and landings.
When maneuvering during slow flight, you are flying very near the stall speed of the airplane. But you don't necessarily have to be flying at slow airspeeds for a stall to occur. A stall can happen at any airspeed and in any flight attitude. This program will explain how to recognize an approaching stall with the power off and the procedures for recovering from a power off stall. Simply stated, a stall occurs when the critical angle of attack is exceeded, causing the smooth airflow over the wing surface to break away. This results in a loss of lift. You practice stalls for two reasons. First, they acquaint you with the stall warnings and handling characteristics of your airplane as it approaches a stall. And second, they develop your skills so you can recover from an inadvertent stall quickly and efficiently with a minimal loss of altitude. Stalls are practiced at an altitude that will allow you to complete the stall recovery no lower than 1,500 feet above the ground. Before starting the maneuver, clear the area. Then reduce power and slow the airplane to the normal glide airspeed. As the airspeed enters the white arc, extend the flaps to the setting used during a normal approach and establish the landing attitude. Once stabilized, smoothly raise the nose to an attitude which will induce a stall. To help determine when your airplane is approaching a stall, there are several cues you should be familiar with. One of these is the decreasing sound as the airspeed decreases. Another cue is the stall warning, which begins around 5 to 10 knots above the stall. This warning may be either a light on the instrument panel, a warning horn, buffeting of the airplane, mushy controls, or a combination of these. As the airplane nears a stall, control effectiveness decreases, and you may feel the airplane begin to shake slightly or buffet. During this time, you still have full control of the airplane, meaning you can still maintain attitude, heading, and altitude. This stage of flight is sometimes called the incipient stage of a stall, or an imminent stall. If recovery is not made at this point, a stall occurs. In a stall, the wings no longer sustain the lift necessary to maintain flight. Once the critical angle of attack is exceeded, the nose will pitch downward. Initiate the recovery by smoothly reducing the angle of attack as you apply full power. As you add power, you'll need to increase right rudder pressure to keep the ball centered in the turn coordinator. Then use the flap retraction procedures specified by the manufacturer. As the airspeed begins to increase following the recovery, gently establish a climb attitude. If this isn't done properly and you increase the pitch attitude too quickly, a secondary stall could occur. Conversely, waiting too long to establish a climb attitude could result in excessive speed and loss of altitude. The correct procedure is to raise the nose smoothly to the proper pitch attitude and climb at the airspeed recommended by the manufacturer. Once you've achieved proficiency in straight-ahead stalls, your instructor will have you do power-off stalls while in a turn. You will use the same procedures as in the previous maneuvers, except you will enter a coordinated turn of approximately 20 degrees before increasing back pressure on the control wheel. Recovery is much like the straight-ahead stall, except that you must level the wings. However, don't level the wings until you've reduced the angle of attack and have added full power. Then, roll the wings level by using coordinated ailerons and rudder pressure. If you're using flaps, they should be retracted, as specified by the manufacturer. Practicing stalls is not meant to increase your ability to stall an airplane, but to help you recognize the onset of a stall and how to prevent it. Or, if one does occur, what procedures to use to minimize the loss of altitude. In addition, by practicing a power-off stall, you'll get a better idea of what can happen during an approach to landing if your attention is diverted from flying the airplane. A power-on stall can occur if you attempt to lift off and climb out at an airspeed below that normally used for takeoff, or if you use too high of a pitch attitude when trying to clear an obstacle. As with power-off stalls, learning to recognize the sensations and visual cues that precede a power-on stall will help you avoid accidentally entering into one. Remember, you should practice stalls at an altitude that allows recovery at least 1,500 feet above the ground. After the area is cleared, reduce power. And as the airplane is slowing to liftoff speed, lower the flaps if appropriate. As the airspeed decreases, increase back pressure to maintain your altitude. When the airspeed has decreased to near liftoff speed, simultaneously add back pressure as you advance the power to the takeoff or climb setting recommended by the manufacturer. The power-on stall is initially performed with the wings level, but to simulate a turn after takeoff, your instructor will also have you enter a 20-degree bank to the left or right. Remember, as you add power and continue to increase back pressure, you must compensate for the airplane's left-turning tendencies by keeping the airplane in coordinated flight. The pitch attitude for a power-on stall will be much higher than for a power-off stall. But, like the power-off stall, you will feel the characteristic buffet just before it occurs. Since you still have control of the airplane at this point, recovery from the near stall condition can be made by decreasing the pitch attitude as you apply any remaining power. Then the wings should be rolled level. When there is no danger of a secondary stall, return to straight and level flight or a climb by retracting the flaps if they were used. However, if you don't recover at that point, the airplane will stall and the pitch attitude will decrease abruptly because of the excessive nose-high attitude. If the airplane is not in coordinated flight when the stall occurs, one wing may stall first, causing a sudden roll as the nose pitches down. If the airplane is slipping to the inside of the turn, the upper wing will stall first. In this case, the airplane might roll in the opposite direction, lessening the bank angle. Conversely, if the airplane is skidding to the outside of the turn, the lower wing will tend to stall first. This results in a steeper bank. If the airplane is properly coordinated, it will pitch down with approximately the same amount of bank. Therefore, you should work to keep the aircraft in coordinated flight as you practice any power-on stalls. As your stall training progresses, you'll be introduced to several aspects of stall spin awareness. Although you are not required to demonstrate spin recovery on your private pilot practical test, you are required to have a thorough understanding of spins and spin recovery techniques. Your training in this area consists of both ground and flight instruction. The ground training portion includes instruction in the areas of stall awareness, spin entry, spins, and spin recovery techniques. Then, as your flight training progresses, further emphasis is placed on stall recognition and recovery, and realistic distractions are introduced during flight at critically slow airspeeds. It's important to remember that actual spin training is not required, and under no circumstances should you practice spins or spin recovery techniques without a certified flight instructor on board. Accelerated maneuver stalls are a variation of power-on and power-off turning stalls. Although not included in the private pilot PTS, your instructor may demonstrate how an airplane can stall at higher airspeeds due to the additional load factors created by a steep turn. For example, in a 45-degree level turn, the airplane's effective weight is 1.4 times greater than in level flight. This means that if the normal stall speed for a particular airplane in straight and level flight with flaps up is 50 knots, it will stall at 59 knots in a 45-degree level turn. Before beginning an accelerated stall, clear the area. Then verify that the airspeed of the airplane is below the published maneuvering speed. This will avoid placing high structural loads on the airplane during the maneuver. Next, roll the airplane into a level bank of approximately 45 degrees and firmly increase back pressure on the control wheel to initiate a stall. Normally, you will recover at the first indication of a stall by releasing back pressure while simultaneously adding full power. Then, use the flight controls to keep the airplane coordinated as you level the wings. A crossed control stall is most likely to occur during a poorly planned and executed turn from base to final approach, and is often the result of overshooting the extended runway centerline during the turn to final. Even though flight proficiency in a crossed control stall is not required, it will be demonstrated to you by your flight instructor. The important thing to understand is not how to perform the crossed control stall, but to be able to recognize its onset and the procedures necessary for a safe recovery. A crossed control stall will occur when you apply aileron pressure in one direction, rudder pressure in the opposite direction, and use excessive elevator back pressure. Stall should be practiced at an altitude that will allow you to safely complete the stall recovery no lower than 1,500 feet above ground level. For this demonstration, we'll check the area for other traffic, reduce the power, then maintain altitude until the airspeed approaches the normal glide speed. Flaps should not be lowered during this demonstration because of the possibility of exceeding the airplane's limitations. Once the glide attitude and airspeed have been stabilized, roll into a medium bank turn to simulate a final approach turn with an overshoot to the center line of the runway. Continue the turn while applying full rudder input in the direction of the turn. Maintain the bank by applying opposite aileron pressure to stop the overbanking tendencies, while slowly increasing back pressure on the elevator to keep the nose from lowering. When the airplane stalls, release the pressure on the flight controls and then increase the power as necessary to return to straight and level flight. In a crossed control stall, the airplane may stall with little or no warning. The nose may pitch down and the inside wing suddenly drop. The airplane may continue to roll into an inverted attitude. This is usually the beginning of a spin and can be very dangerous at lower altitudes. Early recognition of the characteristics of a crossed control stall is very important because recovery may be impossible due to the altitude needed for a safe recovery. The demonstration of an elevator trim stall will show you what can happen when full power is applied during a go-around from a normal landing approach, a simulated forced landing, or immediately after takeoff with an improperly set takeoff trim setting.
Whenever we're practicing stalls, John, one thing you've got to remember according to the PTS is that we must recover from a stall no lower than 1,500 feet AGL.
Even though flight proficiency in an elevator trim stall is not required, it will be demonstrated to you by your flight instructor. The important thing to understand is not how to perform the elevator trim stall, but to be able to recognize its onset and the procedures necessary for a safe recovery. You will also learn the importance of making smooth power changes, how to overcome strong trim forces, and how to maintain positive control of the airplane in a go-around environment. After clearing the area for other traffic, slowly reduce the power. Lower 1/2 to full flaps. Then set the power to idle. Maintain altitude until the airplane slows to the approach glide speed. Once established in a glide, simulating the final approach path to the runway, smoothly advance the throttle to the maximum allowable power as you would in a go-around. To recover from the approaching stall, apply positive forward control pressure to lower the nose, maintaining directional control with aileron and rudder pressure. Maintain forward pressure until a normal climb airspeed and attitude can be established. Then retrim the aircraft to remove excessive control pressures.
It is imperative that a stall does not occur when full power is applied during a go-around from a normal landing approach, a simulated forced landing, or immediately after takeoff with an improperly set takeoff trim setting, because the amount of pitch change and altitude needed for a recovery may be inadequate. From this demonstration, it is apparent that stall recognition is important, and prompt recovery procedures should be implemented immediately to prevent a fully developed stall condition.
After gaining proficiency in stalls, you will be introduced to more advanced maneuvers, such as constant altitude steep turns. This maneuver consists of a constant altitude 360-degree turn with a bank angle of 40 to 50 degrees. The practical test standard, PTS, requires that you be able to turn in both directions. Steep turns help you develop coordination of pitch and bank while maintaining altitude at a constant power setting. They also develop smoothness, orientation, and division of attention. Before you enter the maneuver, make sure there is no conflicting traffic in the area. To maintain orientation, select a reference point parallel to your flight path. Section lines, roads, or a prominent landmark on the horizon are all good reference points that help you determine the starting and ending points of the maneuver. Begin the maneuver with the airplane stabilized in straight and level flight at an altitude that will allow you to complete the maneuver no lower than 1,500 feet above ground level. Your airspeed should be at the manufacturer's recommended speed, or, if none is given, at or below maneuvering speed. Roll into a 45-degree bank turn with coordinated aileron and rudder pressure. This bank should be smoothly established at a moderate rate without rushing. As the bank steepens, you will need to increase back pressure and add power to maintain level flight. If you do not maintain the proper pitch attitude, the aircraft may enter a steep descending spiral. The natural reaction in this case is to increase control wheel back pressure, which only tightens the descending spiral and increases the possibility of an accelerated stall. If you're losing altitude and the pitch attitude is low, decrease the angle of bank slightly, then bring the pitch attitude back up to level flight and return to the desired bank angle. When you roll out of a steep turn to a designated heading or to your reference point, use the same procedures as for shallower banks, but initiate the rollout approximately 20 degrees before reaching the desired heading. As the bank decreases, reduce back pressure to maintain altitude and adjust the power to return to cruise. If you use trim during the turn, the last step is to relieve control pressures by re-trimming the airplane. As you gain proficiency in steep turns, you may learn to continue from one turn to another without hesitation between the two. The back pressure held in the first turn is reduced during the rollout, then reapplied as the angle of bank increases in the turn to the opposite direction. During this maneuver, you will most likely experience an overbanking tendency. This is due to the wing on the outside of the turn traveling a greater distance than the inside wing. Since it is traveling farther, it has a faster airflow. As more air passes over an airfoil, more lift is produced. This increase in lift on the outside wing causes the airplane to roll beyond the desired bank angle. To counter this tendency, you must apply slight aileron pressure opposite the direction of turn. In addition, because the tail of the aircraft is located aft of the center of gravity of the airplane, it does not track in the same arc. To streamline the fuselage, you need to apply rudder pressure. As you practice steep turns, you will begin to gain confidence in controlling the airplane while your attention is diverted outside. Developing this important skill helps you progress easily into the more advanced ground reference maneuvers.
The ground reference maneuvers in this program are designed to help develop your ability to compensate for wind drift and control the airplane while your attention is diverted outside. Many of the skills you'll learn in these maneuvers can be applied to your routine flying and improve your feel for the airplane. The first step in executing any ground reference maneuver is to determine from which direction the wind is blowing. This can be done by noting the position of the windsock at the departure airport, the runway in use, or the direction the wind is blowing trees and dust. Another method you can use is to fly a 360-degree constant airspeed, constant bank turn. The difference between your starting and ending points gives you the general idea of the wind direction. Let's begin with a look at rectangular courses. The procedures you use to fly a traffic pattern are very similar to those you'll use to fly a rectangular course. The exception is that you'll fly at a constant altitude between 600 and 1,000 feet AGL. As the name implies, you'll be flying a rectangle around reference lines on the ground. The objective is to maintain an equal distance from the boundary throughout the maneuver. This distance should be about 1/4 to 1/2 mile. Ideally, one leg of the pattern should be directly downwind. This allows you to fly one segment with the wind, another directly into the wind, and two legs with a crosswind. The preferred entry to the rectangular course is on the downwind leg in straight and level flight. At this point, the ground speed is higher than on any other leg in the pattern, and little or no crab angle is needed. When you're opposite the corner of the field, start the turn to crosswind. Since the ground speed is high, the initial bank angle is steep. But to maintain a constant distance from the field, the bank is gradually reduced as your ground speed slows during the turn. The turn to the crosswind leg is completed so that a crab angle is established into the wind. Maintain a crab angle that will allow you to fly a straight line at an equal distance from the field. The turn to upwind is begun when you're opposite the end of the field. During the turn, your ground speed slows as you head into the wind. Therefore, the angle of bank gradually decreases. This leg is flown directly into the wind, so no crab angle is required, and your ground speed is slow. During the turn to the next leg, your ground speed gradually increases. This means the angle of bank must increase to maintain a constant distance from the field. On this crosswind segment, the wind tends to drift the airplane toward the field. Therefore, the turn is completed so that a crab angle is established into the wind. Maintain this crab angle until you reach the end of the crosswind leg. As you turn downwind, your ground speed increases. This means the bank angle needs to increase gradually throughout the turn to maintain a constant distance. Your ability to compensate for the wind during a turn is an important element of flying a rectangular course properly. S-turns are a series of alternating left and right 180-degree turns across a reference line on the ground. During each turn, a constant radius is maintained by varying the angle of bank to compensate for wind drift. To begin, select a road, fence, railroad, or section line which lies perpendicular to the wind and is long enough for a series of turns. Approach the road on a downwind heading at an altitude between 600 and 1,000 feet AGL. When you're directly over the road, begin your turn. At the entry point, your ground speed is high, so the bank angle is steep. As the turn continues, your ground speed gradually slows. This requires a decrease in the bank angle to maintain a constant radius. As you approach the road, the bank angle continues to decrease until you are in straight and level flight over the road. Begin a turn in the opposite direction without delay. Since the ground speed is low, the initial bank is shallow. In the second half of the S-turn, the airplane is turning from an upwind to a downwind heading. Ground speed increases as you progress, so you'll need to increase the bank angle to maintain a constant radius. The steepest bank occurs as you near the 180-degree point. Once again, you should be in level flight when you're directly over and perpendicular to the road. If the maneuver will continue, immediately roll into the next turn. In turns around a point, you'll fly a constant radius circle around a prominent reference point on the ground. You'll need to adjust the bank angle throughout the maneuver to compensate for wind drift. The point you select should be easy to distinguish, yet small enough to present a precise reference. Like most ground reference maneuvers, the entry is flown on a downwind heading between 600 and 1,000 feet AGL. You should fly to one side of the reference point at the distance you want to maintain throughout the turn. When you're opposite the reference point, roll into the initial bank at a fairly rapid rate. Since you're flying downwind, the ground speed is high and the angle of bank is at the steepest point in the maneuver. During the first half of the turn, the bank angle is gradually reduced as your ground speed decreases. This allows you to maintain a constant distance from the reference point. As you reach the upwind side of the maneuver, the ground speed is low and the angle of bank is at its shallowest point. Your ground speed begins to increase as you continue toward the downwind side of the maneuver. This requires a gradual increase in the bank angle to maintain a constant radius. You may need to fly around the point several times to get a good feel for the wind, varying bank angles, and the proper distance from the reference point. It is also a good idea to practice turns to the right as well as turns to the left.
Most of your takeoffs and landings will be made at airports with lengthy, hard-surfaced, smooth runways. However, you might at some time have to land and take off from short runways or rough or soft surfaces over obstacles, or you might experience any combination of these. The efficiency of your airplane depends on your ability to employ the techniques of maximum performance takeoffs and landings. Although we will discuss short and soft field takeoffs and landings separately, you will find that many times both conditions exist at the same location. When this happens, you might need to use the techniques for both. Let's begin by looking at short field procedures. Short field takeoffs begin with a check of the performance charts to see if your airplane is capable of a safe takeoff under existing conditions. This is extremely important as density altitude increases. Besides considering the runway length and takeoff roll, during training you normally assume that there is a 50-foot obstacle to be cleared after takeoff. This requires additional performance calculations to ensure clearance. The pre-takeoff checklist is basically the same as the one you use for a normal takeoff, except that you set the flaps as recommended by the airplane manufacturer to achieve a maximum performance climb. If runway length is critical, position your airplane so that you can use all of the available runway. Then, align the airplane with the center of the runway and initiate the takeoff by holding the brakes and applying full power. While this does not necessarily shorten the ground run, it does help you be sure that the engine is running smoothly. During the takeoff roll, allow the airplane to accelerate in a level attitude with the elevator in the neutral position for minimum drag. Shortly before reaching the best angle of climb airspeed, positively rotate the airplane. Maintain this attitude until the airplane has cleared all obstacles. If no obstacles are in the departure path, or after you have cleared the obstacles, adjust the airplane's pitch to the normal climb attitude and slowly retract the flaps. You must also apply special techniques when landing on a short field. The objective is to touch down near the approach end in a full stall attitude. For training, you should assume that the approach is over a 50-foot obstacle. Your preparation for the landing begins on the downwind leg of the traffic pattern, where you slow the airplane to pattern speed and extend the flaps to the first position. Apply the remaining flaps as you continue through the base leg.
and after the turn to final. Reduce the airspeed progressively to that recommended by the manufacturer for short field landings. Ideally, you should conduct the final approach at a constant glide angle, airspeed, and power setting. You may need to make minor adjustments to pitch and power to maintain a stabilized approach. If you maintain the proper approach configuration, the airplane will not float above the runway and you will touch down close to the stall speed. To produce the shortest ground roll after landing, you should make sure the throttle is closed. Apply back pressure to the control wheel. Retract the flaps and apply firm and even braking action. Typically, your initial soft field training will take place on a hard surfaced runway. Regardless of the type of practice surface used, soft field techniques are a valuable part of your flight training. If possible, complete your pre-takeoff checklist on a firm surface in an area free from loose sand and gravel. This helps to prevent propeller and airframe damage caused by flying debris. Set the flaps for the maximum performance takeoff as recommended by the manufacturer. With the checklist completed, you're ready to taxi. If the taxi area is soft, hold back pressure on the control wheel to keep the nose wheel from sinking into the ground. You should also add a slight amount of power to help keep the airplane moving. Try to clear the approach area while taxiing in order to keep the airplane moving directly from taxi to the takeoff roll. As you increase power during the soft field takeoff, you'll have to apply right rudder pressure to overcome torque, P-factor, and spiraling slipstream. In order to prevent the nose wheel from sinking into the soft runway during the takeoff roll, you need to transfer the airplane's weight from the landing gear to the wings as quickly and smoothly as possible. This is accomplished by holding back pressure on the control wheel and accelerating the airplane in a nose-high attitude. As the weight on the nose wheel is reduced, nose wheel steering becomes less effective. However, you will still have directional control because of the slipstream flowing over the rudder. You can relax some of the control wheel back pressure as speed builds up and the elevator becomes more responsive. As you lift off the runway, lower the pitch attitude and accelerate in ground effect to the best angle of climb airspeed before initiating a climb out. When all obstacles have been cleared, accelerate to the best rate of climb airspeed. Slowly retract the flaps and continue your climb. As you enter the traffic pattern and complete the checklist, you need to concentrate on performing a stabilized approach with a smooth, soft touchdown. Using full flaps during a soft field landing will help you touch down at a low airspeed. They should be applied smoothly during the downwind, base, and final legs of the approach. Your objective for a soft field landing is to transfer the airplane's weight from the wings to the landing gear as smoothly and gently as possible. The final approach airspeed that you use at a soft field is normally the same as that used for short field landings. The descent angle will depend on whether or not any obstructions are located in your approach path. The flare and touchdown require precise pitch and power control. If runway length is not a problem, you might want to carry a small amount of power during the flare out. Then, as you near the surface, smoothly raise the nose of the airplane to an attitude which resembles the climb attitude. In this way, the airplane will settle onto the ground as gently as possible. Maintain this power and elevator back pressure during the rollout to help keep the nose wheel off the ground as the airplane decelerates. Deceleration on a soft surface is generally quite rapid. Therefore, braking, other than that required for directional control, is usually not needed. Although you need special techniques when operating to and from short and soft fields, your ability to properly execute maximum performance takeoffs and landings will increase your flying enjoyment. The skills that you acquire will not only make you a safer pilot, but will enable you to use the many airports not serviced by long, hard-surfaced runways.
During VFR flight, you control the airplane's attitude and flight path by combining a general view of the horizon and what you see outside your airplane with a cross-check of the flight instruments for specific information. During instrument flight, you rely completely on the flight instruments to provide all the necessary information. Now the Earth's horizon and your outside visual references are replaced by the attitude indicator, which gives you information regarding pitch and bank. Never intentionally fly into IFR conditions without first obtaining an instrument rating. However, developing your instrument flying skills will help you cope with an inadvertent encounter with IFR conditions. As you learn to control an airplane solely by instruments, you'll develop more confidence and increase your skills in instrument interpretation and precision control. One of the first skills you need to develop is a systematic method of looking at each flight instrument. This skill is called scanning. The instruments included in your scan are the attitude indicator, altimeter, vertical speed indicator or VSI, heading indicator, turn coordinator, and the airspeed indicator. During your training, you will learn not to fixate or stare at one particular instrument, nor place too much emphasis on one indication. You will also discover that you cannot omit any instrument from the total scan. For example, if you're trying to maintain directional control by staring at the heading indicator and omit the other instruments, you might place yourself in a critical flight attitude. You can see that it's important to scan all of the instruments. Let's look at how to maintain straight and level flight by instrument reference. The objective is to fly a predetermined heading at a specified altitude. To help maintain the desired altitude, use the attitude indicator, altimeter, vertical speed indicator, and airspeed indicator. A constant power setting helps to simplify maintaining your altitude. The attitude indicator gives a direct indication of your general pitch attitude. Any changes in pitch, whether up or down, will be detected by the attitude indicator. The altimeter tells you whether you're at the desired altitude or moving away from it. For example, if your altitude begins to increase due to an inadvertent pitch change or a vertical air current, the altimeter indicates the change. But the altimeter is not the only instrument that tells you the altitude is changing. The vertical speed indicator also helps detect movement from the planned altitude. The VSI instantly indicates the trend of any altitude displacement. The actual rate of climb or descent, however, may take a little longer to register. Another instrument that indicates a change in altitude is the airspeed indicator. Once you've established a constant power setting, airspeed fluctuations signify pitch changes that will result in altitude variations. For example, if pitch increases, the airspeed begins to decrease. If airspeed increases, pitch has decreased and you will lose altitude. When you notice a change in altitude, you'll need to correct the pitch attitude to return to the original altitude. You should make corrections by referring to the attitude indicator and monitoring the altimeter to complete the adjustment back to level flight. As a general rule, if the altitude deviation is less than 100 feet, you should correct the pitch attitude without changing power. When the deviation is greater than 100 feet, you should combine a pitch change with an appropriate power adjustment. Let's look now at the other half of straight and level flight, maintaining a constant heading. The instruments used for bank control are the attitude indicator, heading indicator, and turn coordinator. The attitude indicator instantly shows any change in bank and gives a general picture of bank attitude. If you bank to the left or to the right, you get a direct indication of the movement on the attitude indicator. During coordinated flight, a turn is also shown on the heading indicator. Generally, if the heading remains constant, the wings are level. A shallow bank is shown by a slow heading change, while a rapid change signifies a steeper bank. Another instrument which provides an indirect indication of a bank is the turn coordinator. Your heading will remain constant when the wings of the miniature airplane are level and the ball is centered. You will be in a bank and subsequent turn when the wings of the miniature airplane roll to either side. With an understanding of how straight and level flight is performed, let's look at how climbs are made by instrument reference. To enter a climb from cruise airspeed, you need to raise the nose of the airplane. Monitor the attitude indicator as you increase the pitch attitude above the horizon reference line. You must also increase power to sustain the climb. Do this either simultaneously with the pitch change or after the pitch has been established and the airspeed approaches the desired climb speed. When the airspeed stabilizes, trim the airplane. During a stabilized climb, any change in airspeed signifies that the pitch attitude has changed. To correct the pitch, use the attitude indicator. Your actual rate of climb depends on the density altitude, power setting, and aircraft weight. But the VSI can provide an indirect indication of pitch changes when it increases or decreases. In a climb, you maintain directional control the same as in straight and level flight, with one exception. The ball in the turn coordinator is scanned to ensure that you are applying enough right rudder pressure. The level off from an instrument climb is performed the same as with outside visual references. As you approach your desired altitude, begin the level off by leading the altitude by 10% of the vertical speed. For example, if you are climbing at 500 feet per minute, lead the level off altitude by 50 feet. To level off, apply smooth controlled pressure until the miniature airplane on the attitude indicator is aligned with the horizon reference line. As you establish a level flight attitude, the vertical speed indicator will move slowly toward zero. The altimeter needle will slow its upward movement, and the airspeed indicator will move toward cruise airspeed. To complete the transition from climb to cruise, relax the right rudder pressure you held during the climb to maintain the planned heading, reduce power to cruise, and trim the airplane. With the airplane established back at straight and level, let's go ahead and look at how to descend by instrument reference. To enter a constant airspeed descent, establish the desired airspeed by reducing power to the predetermined setting and maintain altitude. As you reach the desired airspeed, lower the pitch to maintain the airspeed and trim for the descent. Correct any deviation in airspeed by adjusting the pitch attitude. Use the bank control instruments to maintain directional control during the descent. As you approach your planned altitude, begin the level off by leading the altitude by about 10% of the vertical speed. Raise the pitch attitude to level flight. Then increase the power while maintaining directional control. When stabilized in cruise, retrim the airplane. The next maneuver we'll look at is performing a turn. All turns by instrument reference are made at a standard rate of 3 degrees per second. When the miniature airplane in the turn coordinator is aligned with the reference mark, you are in a standard rate turn. To enter a turn, establish a bank by referring to the attitude indicator. As you become familiar with your airplane, you'll learn the angle of bank that produces the standard rate turn at a given true airspeed. As the turn is established, you'll need to raise the nose slightly to offset the loss of vertical lift during the bank. Then, check the turn coordinator to ensure you are in a coordinated, standard rate turn. If the turn is not standard, make a slight bank adjustment on the attitude indicator and confirm the change on the turn coordinator. The altimeter and the vertical speed indicator must be included in your scan to assure that the altitude is being maintained. During the turn, monitor the heading indicator to determine the progress toward the desired heading. To allow for the route, lead the heading by the number of degrees equal to 1/2 of the bank angle. For example, if you are in a 15-degree bank, start the rollout about 8 degrees before the desired heading. As you return to wings level, release the back pressure held during the turn and continue your instrument scan. Part of your attitude instrument training will include recognition of and recovery from unusual or critical flight attitudes. Your instructor will have you close your eyes and let go of the controls. The airplane will be maneuvered to simulate an unusual attitude that could result from turbulence, preoccupation with cabin duties, disorientation, or erroneous instrument interpretation. When you're instructed to take the controls, you need to evaluate the situation immediately and make a proper recovery. For example, the approach to a climbing stall is signified by a high-pitch attitude and decreasing airspeed. This situation requires you to lower the nose toward level flight while immediately adding full power and leveling the wings. Conversely, if the pitch attitude is low and the airspeed increasing, you'll need to reduce power to prevent excessive airspeed, adjust the wings to level, and then raise the pitch to a straight and level flight attitude. Your initial training in attitude instrument flying does not qualify you to fly in IFR conditions without an instrument rating. However, it does provide you with basic emergency skills if you inadvertently lose outside visual references. It also helps you interpret the instruments more effectively during VFR conditions.
Night flying can offer some of the most exciting and enjoyable flying that you will ever experience. At night, there is usually less traffic. The air is generally smoother, and the communication frequencies are less congested. However, because your vision is less sharp at night, you need to pay close attention to numerous items when planning and making a night flight. Safe night flying begins with careful and thorough flight planning. Because of the visual limitations of night flying, chart references and the altimeter may be your only reliable means of determining altitudes sufficient for terrain and obstacle clearance. You should also have available the adjacent chart if your route of flight will take you near the edge of the sectional. By referring to the adjacent chart, you'll be able to identify distant cities or landmarks not found on the primary chart. Your preparation for a night flight should also include a complete weather briefing, including a study of the available weather reports and forecasts. When reviewing this material, it is important that you pay close attention to the temperature dew point spread. A small spread is a good indication of the possibility of the formation of ground fog. Because aircraft drift is very difficult to detect during takeoffs and landings at night, it's a good idea to also pay close attention to the wind direction and speed. Another important consideration is that under no circumstances should a night VFR flight be made under poor or marginal weather conditions.
As you continue with your planning, it's recommended that you check the availability of en route and destination airport lighting systems along your route of flight. This information can be found on aeronautical charts and in the airport facility directory. It's also important that you check the status of these lights by reviewing the pertinent notices to airmen.
Once your planning is finished, you're ready to pre-flight the airplane. Remember that before any flight at night, you should allow at least 30 minutes for your eyes to adapt to the darkness. To ensure that you completely check the airplane prior to departure, use a reliable flashlight during your pre-flight inspection. You should also have a second, smaller flashlight in the cabin for reading or for use in the event of an in-flight electrical malfunction. As you conduct your pre-flight inspection, avoid shining the flashlight directly into your eyes. This could destroy your night vision, requiring you to readapt your eyes to the dark. Part of your night pre-flight inspection should include a check of all aircraft lighting. Besides assuring that the anti-collision lights are working, you must check your position lights, which are required by regulation for any operation between official sunset and sunrise. These lights help other pilots identify your direction of travel. When doing this, it's a good idea to tap the lens of the light to check for any loose connections. If the light blinks when tapped, the light should be fixed prior to departure. Although landing lights are not required unless the aircraft is operated for hire, most airplanes are equipped with one, and it should also be inspected. You should also check cabin lighting during your pre-flight to make sure the instrument panel is clearly visible. Once you have completed your visual inspection, it's wise to check the ramp area for hazards. Things such as tie-down ropes, chocks, and step ladders are more difficult to see at night, and a quick check of the surrounding ramp area could prevent a mishap during taxi. Before starting the aircraft, take some time to thoroughly familiarize yourself with the location of all instruments, controls, and switches. Fumbling for them in the dark can be confusing and dangerous. While cockpit organization is important at all times, it's especially important at night. Knowing where everything is located will make it easier to find your computer, sectional, or even a pencil. One way to keep from losing essential items in the dark is to use a clipboard or map board to fasten charts, navigation logs, and other essentials in a known location. As an additional aid, be sure your sectional is open to the proper panel and your route of flight is clearly visible. During an engine start at night, use extra caution. In addition to the normal call-out of clear, turning on the position lights or momentarily flashing other aircraft lights will alert others in the area. Before taxiing, especially at an unfamiliar airport, you might want to request taxi instructions. Then, when ready to taxi, turn on the taxi or landing light. Because taxi lights do not cast very wide beams and illumination to either side of the aircraft is limited, taxi speeds should be slower at night. When approaching another aircraft, be courteous and turn the landing light off, if safety permits. This will avoid temporarily blinding the oncoming pilot. As you're taxiing, if there is ever any doubt about where you are or how to get somewhere, don't hesitate to ask. It's also important to remember that when you receive a runway holding or hold short instruction, you must read it back to the controller. Answering with your call sign or Roger is not acceptable. Before taking off, it's important that you conduct a thorough run-up. Since it's not as easy to detect an unintentional forward movement at night as it is during the day, it's a good idea to use the parking brake. By carefully completing all of the items on the checklist, you can detect potential problems which might arise. Before taxiing onto an active runway for takeoff, you should carefully check the final approach course for aircraft. At non-tower airports, it is recommended that you do a slow 360-degree turn in the same direction as the flow of air traffic while closely searching for other aircraft in the vicinity. After ensuring that the final approach and runway are clear of other traffic, you are ready to taxi onto the runway for takeoff. It's important to note that during night operations, ATC will not issue a clearance to taxi into position and hold for intersection departures. During a night takeoff, the runway center line and runway lights provide visual references for directional control. As you begin the takeoff roll, maintain directional control by selecting a reference point down the runway, such as the point where the runway lights appear to converge. Having fewer reference points at night can make it more difficult to establish the proper climb attitude, especially over sparsely populated areas. Therefore, you should use your flight instruments to help establish the proper attitude. As you gain altitude, more distant highways, cities, and lighted areas may become visible. On a clear, moonlit night, it may be possible to determine the outline of terrain and other surface features. Flying at higher altitudes at night will increase your visibility for pilotage, radio navigational reception, and gliding distance. However, you need to consider the existing weather and oxygen requirements at these altitudes. Scanning at night is another important consideration. Although an aircraft's position lights enhance the see and be seen concept, you must not become complacent when scanning for traffic. Unless a conscious effort is made to separate an aircraft's lights from stars or the lights of a city, conflicting traffic can go unnoticed. One way you can help other pilots to see your aircraft is by turning on your landing light. In fact, the FAA is encouraging all pilots to turn on their landing lights when operating within 10 miles of any airport, regardless of the time of day. Another thing that can be very difficult to detect at night is changing weather conditions and cloud formations. Typically, the first indication of flying into marginal weather conditions is a disappearance of stars or lights on the ground. A halo or luminous glow around the position lights or a reflection of the landing and anti-collision lights may indicate you have penetrated an area of haze or clouds. If you inadvertently enter these conditions, you should immediately use instrument references to establish control of the airplane in straight and level flight. Then note your present heading and make a 180-degree turn back to visual conditions. To help avoid accidentally flying into instrument weather, you should continually update your weather briefing by contacting en route Flight Advisory Service or any flight service station along your route. Your concern for changing weather conditions should be combined with careful planning for emergencies. If you need to make a forced landing, finding a suitable field presents special problems. The nature of the surface and terrain is difficult to see, even on a bright moonlit night.
In the event of an engine failure at night, one of your primary considerations should be to plan an approach and landing to an unlighted area. Lighted areas typically indicate structures that may obstruct a landing area.
Although highways may provide places to land, you need to be aware of the possibility of power lines that are often located along and across them. As a safety precaution, many pilots alter their route at night to keep within a reasonable distance of lighted airports for most of the flight.
When planning for an emergency landing at night, one of the primary considerations should include selecting a landing area close to public access if possible.
When approaching an airport at night, it may be difficult to identify the runway layout until you are almost on top of the airport. For this reason, you should fly toward the airport beacon light until the lights outlining the runway are distinguishable. To fly a traffic pattern of the proper size and direction, the runway threshold and runway edge lights must be positively identified. Once seen, the approach threshold lights should be kept in sight throughout the airport traffic pattern and approach. To conclude your flight, the same landing procedures and techniques used during the day are also performed at night. However, runway lights, airport lights, city lights, and the airplane's landing light may create illusions not encountered during daylight. Thus, speed, altitude, and distances may be more difficult to judge. If glide slope information, such as a VASI or PAPI, is available, it will help you maintain the proper descent attitude. By carefully monitoring your flight instruments and power setting, you can help to ensure a smooth approach and landing. You should practice night landings both with and without the landing light to enable you to make a safe landing in case the light fails. Although special consideration is needed at night, Proper preparation and flying techniques will help to make flying at night a very enjoyable experience. Your ability to go from daylight to the night environment will not only add to your airplane's usefulness, but it will also increase the pleasure you receive from flying.